This video is part of an online course of multivariable calculus that I'm going to talk about orientation of a surface in R3. Okay, so what is an orientation and why do we need that? Well, let's go back and look at integral over curves, which we call them line integral. If we have integral of f ds, okay, over a curve C, we parameterize the curve C with respect to t, and then the s in here, it would be the element for arc length. So element for arc length, and then this integral does not depend on parameterization of C. We talked about that before. Of C. But if we take the integral of a vector field over the curve C, it doesn't depend on parameterization of C, but it depends on orientation of C. Well, what is an orientation of a curve? If you have a curve like this, for example, this is the curve C, then the orientation is basically telling you that we're going from the point A to point B in that direction. Basically, this arrow shows the orientation of a curve C. Okay? Now, if we take integral over a surface, we show it by that, the double integral of f ds over surface S. Okay, so we parameterize the surface S by parametric equations R of u and v with two parameters. Then the d capital S here is the element for surface area. And then we say that this double integral does not depend on the parameterization that we choose. Parameterization of S. But the double integral of a vector field over the curve S, it doesn't depend on the parameterization, and both of them actually depend on the orientation of the surface S. Okay, the question is that if you have a surface S, something like, for example, this, how can we define orientation in here? What is definition of orientation of a surface S? Orientation of a curve is just basically the direction on the curve. Is it going from A to B, or it going backward from B to A? But for the surface S, we need a good definition for it. Okay. So, definition. An orientation of a smooth surface. A smooth surface, it means that it's differentiable, it's a very nice surface, continuous. Surface S is a choice of a unit normal vector at each point. Which varies continuously as you move along the surface S. Okay, so let me clarify what it means. So we have a surface S like this, and then at any point, for example, at this point, we have a tangent plane. Okay, a tangent plane is a plane that is perpendicular to, that is tangent to our surface. Okay, for example, this is our tangent plane at this point. Then we have two choices. We can have the normal vector at this direction, or we can have the normal vector at this direction. Okay, so the question is which one to choose. What is the normal vector? Let me give you a recall for that. A normal vector is a vector that is perpendicular. Let me write in here, perpendicular to the tangent plane. At any given point, we have a tangent plane and a normal vector for it, which would be a vector that is perpendicular to that. It's called the normal vector. And we say that it's unique because it has the length 1. Has length 1. Okay, so the question is which direction you choose. The orientation would be basically the choice that you have for the normal vector, to choose this vector that is upward or that vector that is downward. Okay, so that's basically the orientation. And then we say that by convention, we say that one of these orientation, it's positive orientation, and we're gonna be consistent for all of our work and choose that orientation to in our problems. So positively oriented or positive orientation is what? If we have a closed surface. So if S is a closed surface, it means what? It means that S is the boundary of a solid region. S is a boundary of a solid region. Okay, something, for example, you have a sphere, and let me graph the sphere, and S is basically the boundary of the sphere. Let me graph a good sphere for you. Okay, so this is our surface S, and then as you see, at any point, for example, at this point, we have two choices, to choose this one as our orientation or that one as our orientation. Okay, so there are some normal vectors that are going inward to the center of our surface S, and there are some normal vectors that are outward. Okay, then by convention, we say that S has positive orientation if we choose the outward normal vector. So the positive orientation is the one that normal vectors point outward from E. This is E, the solid region E. Okay, so we say that this is positive orientation, and then we say that these ones that are going inside, they are negative. These are positive orientation, these are negative, okay? And if the surface S is not closed, so for any smooth surface S, positive orientation is the one that normal vectors point upward. Okay, so assume that we have a surface S like this, for example. It is not specifically closed, and then at any point we have two choices. So one of them are downward like this, the other one are upward. Okay, some of them are downward like that. Then we say that these ones that are upward, they are positive, and these ones are negative. Okay, so how can we say that it's positive when the kth component, basically the third component in our vector, is positive? When it's positive, it means that it's upward, and basically our surface S has positive orientation. Okay, so let me give you one example. The example is this. Find a unit normal vector. Find a unit normal vector of z equals to f of x and y, and tell, does it give positive orientation? Okay, let's do it. Well, I have z equals to f of x and y. I'm gonna find parameterization of that. To find parameterization, I'm gonna let x to be my first parameter, y to be my second parameter, and z to be f of u and v. And therefore, my parameterization would be u, v, and f of u and v. Okay? And then if you remember, the normal vector for this vector function would be the cross product of partial derivative of r with respect to u and then with respect to v. So let's find r with respect to u, which is 1, 0, and then partial derivative of f with respect to u. I can use also this notation for here. And r with respect to v would be 0, 1, and then f with respect to v. And so r of u, r of v, the cross product would be the determinant of this matrix. On the second row, I'm going to put 1, 0, f with respect to u, and then 0, 1, f with respect to v. And then let's calculate this one. It would be negative f with respect to u. And then I'm going to remove the first row, second column. Then it would be negative f with respect to v, and then 1. Okay, so now I need to find the unit normal vector. That's why I need to divide this by its length to make it unit. Has the length 1. And notice that since u is equal to x and v is equal to y, I can use also f with respect to x instead of writing f with respect to u, because my parameter u is equal to x. Okay, and then negative f with respect to y, and then 1, and then divided by its length, which is f of x squared, f of y squared, and then plus 1. Look at here. The third component, so the k component is 1, which is positive. So that's why n is in the upward, and n is upward, and so it's positive orientation. It gives positive orientation based on convention. Okay. Um, so let me give you just one observation in here. I'm gonna say, observe that I can write this as z minus f of x and y equals to 0. And so in that case, the normal vector would be basically the gradient of g, if I call it a function g, gradient of g, which is what? Derivative of g with respect to x, negative f of x, derivative of g with respect to y, negative f with respect to y, and derivative of g with respect to z is 1. So if you want to memorize that, it would be much more easier. So the normal vector that we define would be the gradient of the g function divided by its length. Okay. Very good. Just one small note, but very interesting note is left, and this is this one. I'm gonna say a note. How many orientations do we have for any surface? If S is connected surface, what do I mean by connected? I mean it's just one piece. Okay, then S has either 2, okay, or 0 orientation. Okay, let me move this one in here. Okay, so what do I mean? So S has 2 orientations. It's like the previous example. So we have like S, this is positive orientation because N is upward, and then for this one it would be negative N, which is downward. Okay, so positive orientation, negative orientation. So these surfaces, they are called orientable because they have 2 sides. Okay, so usual surfaces are like that, but there is one very interesting surface that has 0 orientation. This is called non-orientable surfaces. One of the famous one that has just only one side is the Mobius strip. Mobius strip. To see the Mobius strip, all you need to do is to have a strip and then just glue these 2 sides together, but just make a twist and do that. And in that case, you're gonna get Mobius strip like that, and you're gonna see that we have just one side for this. So it doesn't have orientation, 2 orientations, basically 2 sides. It's called non-orientable surface. Let me show it to you. Okay, now let's make a Mobius strip. Okay, if I take this piece of paper and then if I connect these 2 together, okay, so you see that I have just the regular band. It has 2 sides. Why? It's just because if I start graphing just one line, okay, I come back to the starting point, and on the other side I don't have the line, so I just have the line on this side of the paper. But let's look at the Mobius strip. For the Mobius, I don't connect it like that. I'm gonna make a twist and I'm gonna connect it like this. Okay, This is a Mobius strip. It's non-orientable because it just has one side. Okay, I'm gonna show it to you. I'm gonna start at this point and I'm gonna graph my line. It's gonna take a while. So you see, I'm gonna go back to the starting point. I didn't make a twist or anything. I just connect my line. This is my starting point and I come back to the beginning. But the strange thing is that on two sides I have the line. So as you see, basically my Mobius strip has just one side because I started at one side and I graphed a line and it connects everything. But on the other one, I just don't have the line on the inside. Okay, that's why the Mobius strip is a non-orientable surface. It's just because it has just one side.